Well, in line with this morning's theme, my presentation is going to focus on how our company, DigitalGlobe, is addressing our customers and partners' increasingly complex requirements in this area of sustainable resource measurement, management, and leveraging what we do in terms of data collection and information extraction. For us, indeed, it's not just about observing the Earth. It's about the information we're extracting from the data that we acquire and what we do with it. It's very much about how we apply this in solutions that we are implementing to solve difficult problems at a regional and national level, effectively turning pretty images into actionable insights. So the challenges are clearly numerous, facing our communities and nations. Among many, basically, are growing needs for food, water, shelter, energy, that are creating a new dynamic which is rapidly impacting our current ecosystem. And Earth observation has been playing an important role in allowing us to better understand the effects of our activities on our changing planet. And we at DigitalGlobe believe that we have a unique opportunity to apply our expertise to address these global challenges and make a contribution. Our capabilities are more or less, have developed over time, more or less in line with the evolution that we have experienced in the broader geospatial industry. Initially, it was mostly about resolution. So what exactly can you see? What can you observe? And, well, today quite a lot, actually. DigitalGlobe is operating a constellation of satellites that have resolutions up to 41 centimeter. And our newest one, WorldView 3, which we'll be launching later this summer, will be acquiring imagery closer to 30 centimeter. The focus then shifted to positional accuracy, or can you actually accurately measure what you are seeing on the ground? And again, our image's positional accuracy has been steadily improving through the years, from errors around 23 meter when we initially launched our first couple of satellites into 3 meters today with our GeoEye and WorldView class satellites. Then it was all about speed. Can you get me this imagery quickly? Can you get me this information quickly? Today, following events such as natural disasters, the imagery is being acquired, downlinked, processed, and provided to end users within a matter of minutes. And so finally we find ourselves in the fourth era, which is all about what we've been talking about since this morning. Can you make this data and turn it into actionable insights? Today, after over a decade in operation, we have over 4.7 billion square kilometers of imagery in our library. That's a lot of information that we can extract from it. And as users have started mapping and monitoring the world at unprecedented rates, there's a growing need for algorithms, for capabilities to extract information that is suitable for actionable insight and decision making, and algorithms that can be applied at a very large scale. So this need is driving the geospatial industry and ourselves towards more sophisticated ways of getting the information out and developing systems that allow the exploitation of this information. At the core of it is the imagery. We operate 5 very high-resolution satellites that are going to be complemented, as I mentioned, by one more coming this summer, and GeoEye 2, which we're completing and keeping as a ground spare, ensuring that the flow of data will continue to come in large volumes in the future. And constellation is great, but you also need to complement it with the ground infrastructure to be able to leverage and optimize the collection of content. And so with our, we've deployed recently 12 remote ground terminals, which provide us more access to the satellites, faster access to the imagery, and the ability to collect more of the Earth's surface. Sorry. And so this infrastructure effectively means that we have at our disposal sort of a global monitoring platform. And this enables us to look at very large land use classes, such as urban areas, arable land, very wide forests, that we can monitor multiple times a year, multiple times a season. And from it effectively apply processes to generate information, land use land classification maps for very large areas. The data is very rich, meaning that we're able to provide our users with the highest available spatial, textural, and spectral resolution available, allowing for better feature extraction, identification, and classification. And this is a very potent example, actually, of work we do in forest monitoring, leveraging our Worldview 2's 8 multispectral bands. This enables finer classification and more accurate inventorization of this type of resource down to the individual tree. And the type of work has many impacts, actually. It's within land classification, taxation, monitoring of legal and illegal activities in logging, and also climate change impact analysis. The spectral capabilities of Worldview 2 also enables us to develop new technologies for satellite-derived bathymetry. With primarily focusing on our coastal band, we're able to use it to generate bathymetric and benthic map and nearshore, allowing us water classification application never before enabled at this resolution. And so identification is one step, but then we can take it further by extracting measurements from the objects and from the imagery that we are detecting. In this case, this is volumetric information to determine things like oil reserves in storage tanks. And this is one of the major reserves in the United States, where we acquire frequent imagery, make measurements in the storage facility, and then look at the difference from one acquisition to the next and the variations between acquisition periods. So that's one way to do it. We can apply algorithms that we've developed over very large sets of data. Another way that we've been exploring is also the idea of exposing this data to a crowd of people and enable them with tools that allow them to basically extract the features by themselves. Through the crowd, we're able to place many eyeballs over a given area of interest and interpret the results based on a ranking algorithm, which enables us to separate the good annotators from the less reliable ones. The most recent example of that is when we activated this platform for the search of the Malaysian 370 flight. Very quickly after the event, we acquired a lot of imagery, uploaded it to the system, made it available to our users. Over 7 million participants participated in this campaign, looking at over 800 million map views covering over 200,000 square kilometers of imagery. So that's a lot of eyeballs looking at the same imagery multiple times in order to get the reliability and generate over 6.5 million features that have been tagged by this crowd. So there's a clear hunger for participation in this kind of data creation at the global scale, and something that we're just starting to harness at this level. So the physical geography is one part of it. Another element that we've focused on at DigitalGlobe is the human aspect. Effectively, the specific areas of interest that we are working on, that we study, all have physical attributes, which we've captured through the imagery and information that we generate from it. But there's also a human aspect that can be broadly classified in 13 themes. So religion, medical facilities, communications, economy. And these 13 themes of human geography contain hundreds of subdivisions of layers that broadly define the social, cultural, socio-economical makeup of the area that we work in. And this is something that we focus on very much in collecting this data and standardizing it. One example is data we've generated over Abuja in Nigeria, where we've collected over 3,000 points of interest over the city. So those can be cultural centers, medical facilities, bus stops, 1,600 social cultural polygons, 84 vector and raster layers, all of them describing the social cultural makeup of this region. And this data is aggregated from hundreds of different sources, including some of our proprietary sources basically derived from the imagery. And so once you have the physical geography, once you have the human geography, you have what we've been referring to since this morning as the contextual information that describes the area that you are studying. And leveraging that, you can then start looking at specific event data, and through expertise and specific tools that we are using, start generating geospatial insight from the combination of this contextual data and event data. The methodology is looking at specific existing past events as plotted over a specific area of interest, and then looking at correlation with hundreds and thousands of factors that can be relevant. Infrastructure, demographics, whatever it is, the specific event data will be tracked back to those layers and the ones that are relevant in this case. And then using these correlations, we can then identify statistically similar places where the likelihood is highest for this event to occur again, generating the same type of probability maps that Chris was talking about in the previous presentation. An example of that is the work we've done with global copper theft. So the increase in price of copper in the past few years has created also a growth in the incidence of theft of copper across critical infrastructure, construction sites, buildings, monuments worldwide. And with copper theft on the rise, we've tried to look at the problem at the scale of a city, looking at contextual data and seeing how it relates to that specific incidences of copper theft, understand what the correlations are, and then using those correlations to map areas where this event is likely to happen again. For the people who are looking at this problem, it allows us to effectively reduce their search area, reduce the area that they are looking at where this is likely to happen again, and focus their efforts to counter it onto the areas that are where it's most likely to happen again. And I'll just end up with a presentation of the new system that will add to this capability, and that's our WorldView 3 satellites, which we are planning to launch later this summer. In many ways, it's similar to our WorldView 2 system. It's a high agility platform with panchromatic and 8 multispectral bands. In addition, we're adding 8 SWIR bands, shortwave infrared, and 12 atmospheric correction bands. And the satellite will be flying a little bit lower, allowing us to acquire data at a resolution of 31 centimeters. The addition of the SWIR bands is something that's very exciting, that will enable us to actually get much better results in vegetation classification, general land use, land cover, and mineral mapping, for example. So we're very much looking forward to seeing the type of results we can get out of this new satellite. And this is just a quick example of a simulated WorldView 3 data set in a mountainous mineral region. So all of these developments are clearly creating or generating exciting opportunities for us to start looking at some of these more complex issues that our users are facing. We continue to focus on our core technology, our ability to generate large volumes of data of very high spatial, textural, and spectral significance. We're also intensifying our efforts to derive relevant information from these data sets at a very large scale, and in turn, enabling our customers to address large-scale challenges in methods and speeds that have never been available before. With that,